Okay, let's dive right into this. Welcome to the Explainer. Today, we are tackling what I consider the ultimate challenge, Cambridge physics exams. We're specifically looking at dynamics, and we're covering syllabus codes across the entire board. So whether you're taking 0625, 0652, 0654, 0972, 5054, or even 9702, this is for you. Now, if you've ever found yourself staring at a completely blank past paper, feeling that familiar tension build as the clock ticks down, knowing you actually understand the concepts but just can't seem to get them onto the page the way the examiner wants, well, you're in the right place. Our goal today is actually pretty simple, but it's incredibly powerful. We are going to build bulletproof arguments using stress-tested evidence and ironclad quality control. We're going to completely transform your approach so you can turn raw, unstructured knowledge into maximum marks. Because, let's be honest, Cambridge isn't just testing what you know, they're testing how you think and how effectively you can communicate that process under serious pressure.
So here is our roadmap for today. First up, mass and momentum. Second, Newton's laws. Third, we do the transformation. Fourth, a quick interactive workshop. And finally, we'll lock down collision systems. Let's get to it.
Act 1. The challenge. Let's start by looking at some basic definitions that trip everyone up. Okay, let's look at a classic exam pitfall. Imagine two students. First, we have Alex. Alex absolutely loves physics, right? But he just overloads his answers with raw facts and zero analytical structure. Then we have Sam. Sam knows the math inside and out, but he rushes and he completely misses the specific command words in the question. Both of them are throwing away critical marks on the most basic stuff. Take Alex's first major mistake, mixing up mass and weight. In everyday life, sure, we swap those words all the time, but in a Cambridge exam, that is a guaranteed red mark. Mass is a base quantity. It's measured in kilograms, and it's basically the fundamental property of an object that resists any change in motion, inertia. Weight, on the other hand, is a force. It's the literal gravitational pull acting on an object measured in newtons using the formula W equals mg. To put that into perspective, a mass of 100 grams, so 0.1 kilograms, has a weight of about 0.981 newtons here on Earth. But if you take that exact same mass to the moon, its weight plummets to just 0.16 newtons. Why? Because the gravitational field strength on the moon is only about 1/6 of what it is on Earth. The mass hasn't changed one bit, but the weight absolutely has.
And that brings us to our next foundational trap, courtesy of our friend Sam, momentum. So momentum is defined as the product of mass and velocity. P equals m times v, and the unit is kilogram meters per second. But here is the absolutely critical detail that Sam rushed right past in his calculations. Velocity is a vector. That means it has a magnitude and a direction, and because of that, momentum is also a vector. Think of it this way. If you've got a 2-kilogram object traveling at 3 meters per second to the right, its momentum is 6 kilogram meters per second. Simple enough. But if that exact same object is traveling at the exact same speed in the opposite direction, its momentum is negative 6 kilogram meters per second. Sam lost easy, high-value marks just by forgetting that single, crucial negative sign for objects moving the other way. You've got to remember the vector nature of momentum. It is literally the silent killer of exam grades.
Moving on to Act 2, the strategy reveal. It's time to master Newton's laws.
Let's quickly break down the mechanics of the first and third laws. So, Newton's first law tells us that an object will just sit there at rest or keep moving with a constant velocity unless a resultant force acts on it. And honestly, this is super counterintuitive. Down here on Earth, friction tricks us into thinking we always need a continuous force to keep something moving. But out in the vacuum of space, a rock will just drift in a straight line forever, without any applied force at all. Then we have Newton's third law. You know the drill. If object A exerts a force on object B exerts a force of equal magnitude in the opposite direction on object A. But listen closely, because here is the golden rule examiners actively hunt for. These pairs of forces must be of the exact same type. If you jump off a wall, the Earth's gravity pulls you down. But guess what? You are also pulling the Earth up towards you with an equal-sized gravitational force. The Earth's movement is just negligible because it's so incredibly massive. If you push a wall, the wall pushes back. The forces act on different bodies, they're equal in size, opposite in direction, and they are identical in nature.
So how do we structure these arguments perfectly to get full marks? We use the Peel framework. Point, evidence, explanation, link. You make your point directly addressing whatever command word is in the question. You provide your physical evidence or data.
You explain the underlying physics principle, and finally, you link it all back to the specific context of the question. Before we continue and dive into the hardest of Newton's laws, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's decode Newton's second law together. Step 1, force is literally the rate of change of momentum. Mathematically, we write this as F is proportional to delta P over delta T. And when we're using base SI units, that constant of proportionality just happens to be 1. Step 2, well, we know momentum, P, is mass times velocity. Now, if we assume the mass of the object stays constant, which it almost always does in these exams, the change in momentum is just that constant mass multiplied by the change in velocity. Step 3, that brings us to F equals m times delta V over delta T. And since the change in velocity over time is the literal definition of acceleration, we can just isolate acceleration to get the famous equation F equals ma. This is a brilliant derivation because it shows that the larger the mass, the smaller the acceleration for any given force, which perfectly proves that mass is the resistance to a change in motion.
Act 3. The transformation. Let's fix those flawed answers from earlier.
Let's see how structuring the math with Peel turns a fail into an A-star. On the left here, we've got a massive 20,000-ton cruise liner cruising along at 6.0 meters per second. First things first, Alex needs to convert those tons into kilograms, so that's 20 million kilograms. Then apply P equals mv. 20 million times 6 gives us 120 million, or 1.2 times 10 to the power of 8 kilogram meters per second. Boom! He's applied his evidence and explicitly linked it back. Now look at the right. Sam is analyzing a tiny 45-gram golf ball that's decelerating to a stop over 3.0 seconds from an initial speed of 4.0 meters per second. Sam has to convert those 45 grams to 0.05 kilograms. The initial momentum is 0.18. The final momentum is 0. Using force equals change in momentum over time, F equals negative 0.18 divided by 3, which gives us negative 0.060 newtons. And hey, that minus sign? It is not an error. It's the absolute core of the Peel explanation, proving that the frictional force is acting in the opposite direction to the velocity.
Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
Welcome back. Act 4, Interactive Workshop. It's time for a high-pressure data scan.
Okay, pretend you have a 60-second countdown ticking in your head. Challenge 1. We need to extract the core trend from these terminal velocity curves for a shuttlecock and a tennis ball that are both falling from rest. Look at point A. Both objects start with the exact same acceleration, little g, because air resistance is basically 0 right when they drop. But check out points B and C. Notice how the shuttlecock's curve flattens out way earlier? That's because it has a tiny weight and a high drag coefficient, so the upward drag force equals its downward weight much sooner. It literally stops accelerating and hits terminal velocity right at point C. Meanwhile, over at points D and E, our much heavier tennis ball just keeps accelerating. It takes significantly more time and much higher speed until its drag force is finally big enough to match its heavier weight, meaning it hits a much higher terminal velocity at point E. Understanding this constant dynamic battle between weight and drag is absolutely essential if you want those top marks.
Let's move to challenge 2. Find the flaw. Read this scenario very carefully. It says, total momentum before equals total momentum after. Object A is moving right and object B is moving left. But the student has written out the sum of their momentums using purely positive numbers. So, what is completely missing from this calculation? Yep, you guessed it, the negative vector sign. Because object B is traveling in the exact opposite direction, its velocity has to be entered as a negative value. If you don't do that, your entire conservation of momentum calculation just collapses. The sum is going to be completely wrong, and the examiner will immediately cross it out. It is literally the most common trap in all of dynamics. So let's look at how to actually do this correctly. On the left, we have a head-on collision where we've defined left to right as our positive direction. We've got a 2.0 kilogram mass moving at 3.8 meters per second, colliding with a 3.0 kilogram mass moving at negative 4.0 meters per second. The total momentum before the impact is negative 4.4. If they stick together after they crash, their combined mass is 5.0 kilograms. So, negative 4.4 equals 5 times v. Divide that out, and the final velocity is negative 0.88 meters per second. That means the combined mass is moving right to left. On the right, we're looking at an inelastic trolley collision. A 0.20 kilogram glider moving right hits a 0.25 kilogram glider moving left, and they stick together. By strictly enforcing those vector directions we just talked about, we calculate a final joint velocity of 0.49 meters per second. The big takeaway? Momentum is always conserved, as long as there are no external forces acting on the system.
Act 5, the final system. Let's lock down elastic versus inelastic interactions. Let's instantly contrast the kinetic energy states here, because this is a massive stress-tested cheat sheet for you. In a perfectly elastic interaction, not only is momentum conserved, but the total kinetic energy is also perfectly conserved. And here is an incredibly useful trick for your exams. In a perfectly elastic collision, the relative speed of approach before the impact is exactly equal to the relative speed of separation after the impact. Seriously, keep that rule in your back pocket. Now contrast that with an inelastic collision. Here, some of the initial kinetic energy gets converted into other forms, like internal energy, heat, or sound. The total kinetic energy actively decreases. Just imagine two identical trolleys smashing and sticking together. Momentum is absolutely conserved, but a huge chunk of kinetic energy is lost to the environment. Bottom line, kinetic energy might change, but momentum is always conserved in both types of interactions.
Now, let's take all of this to the next dimension with a glancing 2D collision. When two objects don't hit head-on, they bounce off at angles, right? The law of conservation of momentum still perfectly applies, but now you have to resolve the momenta into two perpendicular directions, usually parallel and perpendicular to whatever the initial line of motion was. Think about it. The vertical momentum before the collision was 0, which means the vertical momentum after the collision must also sum to 0. And I'm going to give you a massive study tip right now that will save you so much precious time in the exam hall. A glancing elastic collision between two equal masses always results in those two masses moving off at exactly 90 degrees to each other. They will be perfectly perpendicular. Memorize that rule, especially for the multiple choice paper.
So, bringing it all together, here is your complete physics answering system. Step 1. Command word decoding. You need to know exactly what calculate, explain, or state actually requires from you. Step 2. Apply the Peel framework to structure your math and your concepts so you don't lose those crucial vector signs. Step 3. Utilize a time management matrix so you don't end up rushing like Sam or overwriting like Alex. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCS and click that bell. Don't let another exam pass you by.
And that brings us to the very end of our explainer. Now, I want to hear from you directly. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Also, I'll leave you with this to chew on. If momentum is always conserved in the universe, where did the initial momentum of the Big Bang come from? Think about that. Like and share this explainer with a study partner. Ace the Exams. Your Cambridge success starts here. Keep analyzing, keep practicing, and I'll catch you in the next one.